Okay, thanks for everybody who came back. Today we have no new theory. Well, we do have some new theory, but they will be built in solving some exercises, which is, of course, one of the best ways to learn. If you do exercises, if you have to think about the questions itself, then you learn faster than just by reading the textbook. Okay, so today we have 4 exercises from Etienne McDonald to go over. These are sometimes challenging, so it's best to try it out on your own. You can also look at my solutions if you want. So to start, this is question 3.5, question 5 in chapter 3 from Etienne McDonald. So it says that if A is a ring and such that for every prime ideal P, the local ring A localized at P has no non-zero nilpotent elements, then A has no non-zero nilpotent elements. So again, this idea goes back to this idea of localizing again. So having no non-zero nilpotent element is a sort of a local property. If it's true for every localization, for every prime P, then it's true for the ring itself. And then another question is, if each localization of A at a prime P is an integral domain, is A necessarily an integral domain? So let's start with the first question. So let A be the ring in the hypothesis. So let's try to prove the contrapositive. So let's say that A has no, let's say A does have a non-zero nilpotent element. I'll call that X. So X is a non-zero nilpotent element of A, and let's say X to the M is 0 for some positive integer M. So the question is, does that mean that we can find a prime P such that A sub P, A localized at P, has a nilpotent element? The answer to that is yes. So this is the same exact proof we did last week. So let I be the annihilator of X in the ring A. So X is non-zero, meaning the annihilator is proper. It's a proper ideal because 1 times X is not 0. It's X, it's not 0. And so I is a proper ideal. We can find a maximal ideal M that contains I. Great. So let's localize at this M. So if we localize the ring A at the prime ideal M, you'll have another ring of fractions of the form A over B, where A and B are elements of A, but B is not an element of M. You have to be careful of that. So note that X over 1 is an element of A localized at M. So this X over 1, I claim, is a non-zero nilpotent element. So let's first show that X over 1 is not 0. If I assume it is 0, then there is an S not in M such that S times X is 0, but that's a contradiction because S would be both in I and not in M. Because M contains I, we have a contradiction. So first of all, X over 1 is non-zero. So is it nilpotent? This is obvious. So it's not 0, same power makes X over 1 equal to 0 as the one that X to the M equals 0. So X over 1 is a non-zero nilpotent element of A localized at M. So the first question is done. So now the second question, let's go back. So if each A localized at P is an integral domain, does that necessarily mean the ring we started with was an integral domain? So the answer to that is no. So let's show you why. So consider a Z mod 6Z. So the Z localized is 6. Z mod up by 6. So there are 2 prime ideals of Z mod 6Z I have to take into consideration. They're the localized forms of 2 and the localized form of 3. So if I localize A at 2, if I localize A at 3, I claim they're both integral domains, but of course our original ring A is not an integral domain, so that would be an example that shows the second question is not true. So let's look at elements in A sub 2 or A sub 3. So if I have two fractions, A over B and X over Y, that multiply to 0, then that means there's an element S that's not in the prime P, let's call the prime P, such that S times A times X is 0. So S times A times X is an element of the ring A, Z mod 6Z. So S times A times X is 0 as a product of integers if 6 divides S times A times X. So let's break it into cases. If you have the prime at 2, then the fact that S is not in P means that S is odd, not even. So if 2 divides SAX, that means 2 must divide AX. So that means either A is even or X is even, but that doesn't matter because if you have any fraction with an even numerator, then 3 times that fraction gets you 0. But that means that the fraction itself was 0 to begin with. So if the case is P is equal to the prime 2, then A sub 2 is an integral domain, and the same case if the prime is P equals 3. So you can do the same thing. If you have S times A times X is divisible by 6, and so now in this case, S is not divisible by 3, so 3 is still a prime, so 3 has to divide A times X. So 3 either divides A or 3 divides X. In either case, if you have a numerator which is a multiple of 3, then that fraction itself is already 0 because you have 2, the number 2, which is not in the prime 3. 2 times that fraction will be 0. So you have A localized at 2 and A localized at 3 are both integral domains. Those are the only two primes we have to worry about. So A sub 2 and A sub 3 are both integral domains, but the ring we started with was not an integral domain. So that proves that the second question is not true, it's false. Okay, so that is the first question for today. Okay. So the next question gets a little bit trickier. We introduce. So now we talk about like a set where you have a maximal element. So let A be a non-zero ring and sigma be the set of all multiplicatively closed subsets S of A that do not contain 0. Let's show that sigma has maximal elements, and a maximal element in sigma is of the form A complement S, where A complement S is a minimal prime ideal of A. So how do we do this? So I will first try to show that in this case, we can in fact find maximal elements. This doesn't have anything to do with the proof first, but I just wanted to show you that maximal elements do exist in sigma. So let's take a totally ordered chain in sigma. So these sets Si are multiplicatively closed subsets of a non-zero ring A, which do not contain 0. I claim the union of the elements of the chain is a maximal element in sigma. How do we do that? Well, first of all, I have to prove that sigma bar does not contain 0. But if it does contain 0, then one of the elements in the chain contains 0. That's not true because that's by assumption. Next, I have to prove that S bar is in fact multiplicatively closed. So if you have two elements X and Y in S bar, I need to prove that the product is an S bar. So let's say X and Y are an S bar. They're in one of the elements of this chain, let's say Si and Sj. And because it's a totally ordered chain, let's just say I is smaller than J. So let's say that both x and y live in S sub j. So the product lives in S sub j because S sub j is multiplicatively closed, but S sub j already lives in S bar. So S bar is in fact multiplicatively closed and hence, in fact, an element of sigma. So S bar is in fact a maximal element because if there's an element in sigma that contains S bar, then S bar is just one of the elements that S bar is the union of because it lies on that chain. It doesn't have anything to do with the proof that we're going to do, but it's good sometimes to convince yourself that maximal elements of a set in fact exist before you try to classify them. Let's try to prove the question. So let's say S is a maximal element of sigma. I need to prove that the complement is a minimal prime ideal. So first, let's prove that it's an ideal. Next, let's prove it's actually a prime ideal. And then finally, let's prove it's a minimal prime ideal. So these are three separate questions. How do we prove it's an ideal? So I have to prove first that it is closed under addition. So let's say let's say x and y are not in, let's say they're not in S. That means they are in A complement S. I need to prove their sum is in A complement S to prove it's an ideal. So this is a rather strange proof. So look at this S tilde. So think about all multiples of S and a power of X. So S tilde contains 1. So sorry, I had to prove before that multiplicatively closed subsets contain 1. So S tilde clearly contains 1 because S contains 1. S is clearly multiplicatively closed because the ring is commutative. You can just shift things around. And also, S tilde contains X, but S does not contain X. That means that S tilde properly contains S. If S is a maximal element of sigma, that means S tilde cannot be an element of sigma. So that means S tilde has to have a property that is not in sigma. That property, in this case, has to be that it does not contain 0, because S tilde is already multiplicatively closed. There's only one way it's not in sigma. That's if S tilde contains 0. So what does that mean for S tilde to contain 0? That means that there's some Sx and some power Rx such that Sx times x raised to the power of Rx is 0 for some Sx in S and some integer Rx. Okay, so we're halfway through the problem. Let's start all over, but instead of x, let's use y. The same thing is true. Okay, how do we prove the sum of x and y is in A complement S? How do we prove x plus y is not in S? So consider Sx x sy times the sum of x and y to the Rx plus Ry power. So by the binomial theorem, you can expand this, and then you'll see there's just finite linear combination of elements of the form some integer n, Sx, Sy, and then some power of x and some power of y, such that their powers add to Rx plus Ry. If you do a little bit more logic, you'll see that either Ra is greater than or equal to Rx, or Rb is greater than or equal to Ry. That means Sx, x to the Ra power is 0, or Sy, y to the Rb power is 0. In other words, that you have this original sum, Sx, Sy, x plus y to the Rx plus Ry, that's equal to 0. And that's bad, because that means if x plus y is in S, then 0 is in S. That's a contradiction. That means that 0 can't be in S, so that means x plus y can't be in S, meaning x plus y is in A complement S. That's exactly.
Hold on. So I'm a little bit confused. So
Mhm.
what if x plus y belongs to S? So
So,
why 0 must be in S?
so, uh, so 0 is not in S. That's a
Yes,
condition of being in sigma.
got it, got it. So why under the assumption that x plus y belongs to S, that implies 0 must be inside of S.
So so look at this product. I don't know. Can you see on this screen?
Yeah, I can see it.
This is actually equal to 0. This is equal to 0. This,
Uh,
yeah.
uh, got
Slides.
it,
I'm sorry. This is
got
not
it.
how to. This is not a good way to do math.
I got
Slides.
it, got it. Understood.
Slides. Yeah,
Yeah,
this is
thanks.
why. Okay. Okay. So x plus y cannot be an S, but that's good for me. That's what I want to prove. Okay. So the first condition of being an ideal is proven. So it's closed under addition. Okay. How do you prove it's closed under multiplication? Okay. So now let's say A is not an S, and let's say X is in the ring. How do you prove that A times X is not an S? You do the same exact thing, same exact thing. So if you do the same exact thing, you see that S tilde again contains a 0. So some Sx and some power Rx multiply together to get you 0 like before. If we assume Ax is an S, then this Ax term is an S, this Sx term is an S, and so the power of Ax to the Rx power is an S, their product is 0. That's bad. So we can't have Ax to be in S. Okay, so it proves that A complement S is an ideal. It's in fact an ideal. Okay, how do we prove it's a prime ideal? So if we have that S is a maximal element, then the complement is an ideal. To prove that it's a prime ideal, it's very simple. Let's say X and Y are not in A complement S. That means they're an S. So their product is an S because S is multiplicatively closed. That means their product is not in A complement S. That's exactly what we need to prove that A complement S is a prime ideal. So we're done. How do you prove that it's a minimal prime ideal? How do you prove it's a minimal prime ideal? So now let's start over. Let's say P is a prime ideal that lives inside a complement S. I need to prove they're equal. If this is the case, that means S is in the complement of P. So you can check that if A complement P is a multiplically closed subset of A that does not contain 0, then by the maximality of S must have A complement P is S, because A complement P is now an element of sigma. But because S is maximal, A complement P and S must be the same. So that means the complement of S has to be equal to P. And that's exactly what we had to prove. A complement P is I'm sorry, this is a mistake. This should be A complement S. A complement S is a minimal prime ideal of A. That's exactly what we had to prove. So that is one part of that question. So we proved from left to right. So we proved that if you have a maximal element of sigma, then the complement is a minimal prime ideal. The other direction is much quicker. So let's prove the other direction. Let's say S is some element of sigma. It doesn't have to be maximal, but I'm saying the complement in A is a minimal prime. I need to prove that S is maximal in sigma. So let's suppose sigma prime is the maximal element of sigma that contains S. So do everything we just did 10 minutes ago. And so that means that the complement of S prime is a minimal prime ideal. And so if S is contained in S prime, the complement of S prime is contained in the complement of S. But then they're both prime ideals, but A complement S is minimal, so they must be equal. And so then to start off, S has to equal S prime. So we're done. Is that good? Any questions?
I'm just thinking that from the less than sentence, so S must be S prime. So got it. Yeah, got it.
Because S is contained in S prime, and if their complements are equal, they must be equal. There's no other way. Okay. Yeah, these are very technical questions, and the most technical is this one. So this is a new question. So I think this is the last question for today. Yeah, it is. So let's start off talking about a new idea. Let's talk about a saturated set. So a multiplicatively closed subset S of a ring A, I will say saturated if product of two elements is in S if and only if both of them are in S. So if you are a prime ideal, the product of two elements is in the prime ideal if and only if one or the other is in the prime ideal. In this case, a saturated set, it means both of them have to be in the prime ideal. So we have to prove a couple of things. So S, let's say, is saturated if and only if the complement is a union of primes, and if S is any multiplicatively closed subset of A, there is a unique small saturated multiplicatively closed subset I'll call S bar that contains S and that S bar is the complement in A of the union of prime ideals which do not meet S. So by definition, from now on we'll call S bar the saturation of S. And for a final question, if you have I as an ideal, what is the saturation of 1 plus I? Okay, let's get started. So let's prove S is saturated if and only if the complement is a union of prime ideals. Well, they already gave us some direction to prove this. So let S be a saturated subset of A. Let this weird German J be the set of primes which do not intersect S. So I claim that the complement is the union of those primes which do not intersect S. So clearly we have containment from right to left. If you're an element of a prime that does not intersect S, then you live in the ring, but not in any, don't have any elements from S. Easy. But let's try the other way around. So before I start the other direction, let's kind of understand an easier way to prove this using localization. Let X be any element of the ring, and suppose all the primes that contain X intersect S. I need to prove that X lives in S. So I kind of prove the contrapositive a little bit. So let's look at X over 1 in the localization of the ring at S. I'll say X over 1 is a unit if and only if there is some Y over S that multiplies by X over 1 to give you 1. But that means there's an element S prime in S such that S prime X Y is S. But that means that eventually S prime X Y is an element of S. By the fact that S is saturated, and you have three elements are in S, three elements products is in S, the product of three elements is in S, that means each of them have to be in S. So S prime is in S, that's already known, X is in S, and Y is in S. But let's focus on the fact that X is in S. So this actual if and only if means that all I have to do is prove that x over 1 is a unit in S inverse A. That's all I have to prove. So to prove that the other direction, left to right, if I want to prove that x is not in S, then it's in one of these primes. It's the same as proving if x is in none of these primes, P, then x is in S. That's exactly what we proved with this unit idea. So let's try to prove this. So let's prove that this element x over 1 generates a non-proper ideal. So all ideals of S inverse A are of the form S inverse I for some ideal I in A. So we have that S inverse I is an ideal containing x over 1 if and only if I is an ideal of x, and also S inverse I is prime if and only if I is prime. As the primes that contain x also meet S, because that's what we assumed, we have that all the ideals that contain x over 1 are not proper. Because if you look at the localization of a ring at S, the ideals that have an element from S will have a unit. But that means that x over 1 must be a unit, and therefore x is in S. And so we are done. So that's proof in two directions. So let's move on to that second question. To review the second question, it's a little bit more complicated. So how do we construct the saturation, and how do we prove what characterization, how to characterize it? So from the second question, for the second question, I just need to prove that S bar is in fact saturated. But that is clear from the first question if we prove that it is a union of prime ideals. So first of all, look at the idea of S bar. I need to prove that it contains S. That's one of the things it said. So let X be in S. If I claim by contradiction that X is not in S bar, that means that, oh, I'm sorry, there's a mistake. This should be that X is in, here it says X is in this union of prime ideals. So that means X is an element of a prime ideal that does not meet S. But that's a contradiction because X is already in S. That doesn't make sense. So already we have containment. It's not that hard. So let R be a saturated subset of S bar that contains S. I need to prove they're equal. I need to prove S bar is the smallest saturated subset of S. Smallest saturated subset, smallest saturated set that contains S. So first of all, R, like S bar, is a complement of a union of prime ideals. So oh my God. It got cut off. I forgot to include it in the slides. I'm so sorry.
No, it's fine.
The answers, I knew I made a mistake.
So as long as you cannot complete it, then you can stop over here and we can continue from here next time.
Let's actually go to the other. I have one question we can do. If we assume the answer, oh my God, it's so silly. If we assume the question 3.7 is correct, can do this question. I knew I was rushing and I was bound to make a mistake. So let's try to find the saturation of 1 plus an ideal I. Sorry. So let I be an ideal and let S be 1 plus I. I claim the saturation of S is the complement in I of the union of the prime ideals which do not meet S. Then that's the same as the primes that do not meet S are the primes that contain I. It's very easy to see. If a prime contains I, then it cannot contain anything 1 plus I, because then you'll have 1. And if a prime P meets 1 plus I, then it cannot contain I, because then it will contain 1. Again, so you can't have a prime ideal that contains 1. So that means the saturation of S is a complement in A of the union of all the primes which do contain I. And that's it. So that's the saturation of 1 plus an ideal. Okay, so I guess we have to stop because I have nothing else, unfortunately. I'm sorry.